going to go to the next speaker. François Pitié is an assistant professor at Trinity College, Dublin, specialized in video processing and computer vision. He received the Google Faculty Research Award, holds several patents, and developed algorithm used by Google Foundry and Weta Digital worldwide. And we also have Vibhoothi. He's a PhD student at Trinity College, Dublin. He's currently co-chairing the extended color format focus grouping Alliance for Open Media for the next generation media video model codec. He's also a member of VideoLAN and xifph.org Media Foundation. So let's welcome.
Thank you very much. So I'm François, and Vibhoothi is here. And so we'll be talking to you about the use of AV1 in virtual production. Yes, so we are from the SIG Media group at Trinity College, Dublin. This was founded by Anil Kokaram here some time ago in '98. And we're covering all the aspects from video processing, spatial audio with Niels Peters, I think is involved in AOM as well. Speech technology, especially hand gestures and speech understanding, and also all the way to hardware implementation on FPGAs. So in the video part, we've been mostly talking to people like you, okay, in recent years, but also we have a past where we've talked to this company called Foundry. We designed a lot of post-production tools for the VFX industry, and received a side tech for that. And basically, we always had this interest in making tools for the movie industry. So I see with great patience that the idea of denoising and adding noise is making its way all the way, not only in film production, but also in streaming. These are 3 examples of stuff we do these days. So on the bottom left, you have real-time, low-power video denoising. And the idea we have is like how to go against the wave and trying to not use the biggest possible machine learning AI model in the world, and instead trying to make it as small as possible and still reach state of the art. On the top left, you have work we had on using post-processing filters to enhance compressed data. And on the top right is work we're doing on trying to use AI to optimize our transcoding parameters. Right, and so today we want to talk to you about virtual production. Quick question, who hasn't heard of virtual production? Who is not familiar with virtual production? Nobody, right, wonderful. So you're all familiar with it, and so this was popularized with Mandalorian. The idea we have these big LED panels here, walls, and they will display the background instead of a green screen. Now, people want to use that for a number of reasons. One of them is that green screen is surprisingly hard to deal in post. You would think this is a solved problem. This is not. This is super hard. That's why you have armies of artists in post-production houses trying to fix all the spillage and all the green stuff we have to remove from the film. And so when you have LED walls, what you have is, well, you have the perfect color, right? And it allows you also to deal with very complex illumination. So if you have reflections and transparency and so on, if you have a green screen, it will take you ages to get right. But here you have something for free immediately. And you have immediate reference for the actors and the film producer as well, so they're very happy to have that on set. Now, you have some downside. It's super expensive, and it takes a lot of preparation time as well. This is the principal camera that will be filming the actors in front of the LED walls. You have other witness cameras that would film different parts and reference points. And you'll notice as well that you have the LED wall that gives you a very nice reference lighting setup. You always have some secondary lighting setup on set to be able to properly lit the people, the actors. That will cause all sorts of troubles afterwards, of course, because you have contaminations of light on the LED panels as well. which is really nasty. And the point is, like, while you're going to be shooting, you're going to have the on-disk footage that you pre-recorded most of the time, or you have, say, a game engine like a Unity engine that will kind of render on the fly for you the reference frame in the background, and then you'll be controlling what you see in camera and what you see, of course, what you send to the LED panels. All right. So what we thought was the problem here is, like, as usual, in production, they want to work with the most pristine quality because they pay by the pixel. And when you talk about compression to them, they're not happy. So they want to work with near lossless compression. So they're using HAP and HLC, which are quite fat. So we're talking like gigabits of bandwidth for HD content. And typically what would happen is, like, it's all fine, but just the transport of it is an issue, because if they're filming something, say, in London, and they need to change something in the background plates, they need to talk to their VFX team in LA, and they need to get that back, and just to get it back to them will take a number of hours, maybe, just to get that, terabytes of data to them. So what we thought was that it would be a very interesting use case for us to see how we could push adoption of AV1 for this particular use case. All right. The first question we had, of course, was like, we need to get some buy-in from them, and we need to prove that AV1 doesn't bring any degradation that they wouldn't be happy with. So we were in contact with, we collaborated with this company called These Guys. They provide systems for these virtual production setups. They're the one, they were involved in the Sphere in Las Vegas. So they mainly do live entertainment, but they also do virtual production setups. And so this is their setup, in-house setup they have. Now their in-house setup is not the highest quality, because really their clients have the very expensive setups, so they have whatever they can, but still very representative of what they would have. So they have a 6K camera that is Genlock with a screen, and we have a capture at 30 frames per second of the system. And what we're trying to do here is to basically do a simple control experiment here, like to send to the background compressed streams at different levels of compressions and algorithms, and trying to see whether we can notice any difference in the in-camera footage. So on the top left, you have the setup, the camera filming the background. On the bottom left here, you have the on-disk footage that is being compressed. The bottom right, you have what the camera sees, right? And the top right, you have a mask. Usually they use this mask because they will do something called set extension, which is basically they will add the composite, an extension of the background to fill in the gap here. You'll see the first thing that will kind of strike you is the color is different, okay? And that's something that they will be struggling a lot with. Like, it's one of the key pain points in virtual production, is that you have lengthy protocols to tweak your LED panels, tweak your camera LUTs to make sure that it kind of lines up as neatly as possible to the original footage. And it turns out to be very tricky. The quality, of course, is a bit different. And also, you can see this little QR code that we added at the bottom. I don't know, you can see little black and white codes here. This is just because the Genlock setup, even so it's a professional studio, was not really perfect, and so we had issues of mismatches of frames at render. Typical problems of production. It's always perfect when you see it in Netflix, but it's in real production world, it's like messes everywhere. I don't know if you're familiar with that. This is Moiré. This is the problem you have. This dates back from 1940s, but that dates of when you didn't have tapes, and we had to film TV screens with your film camera and trying to transmit data like that. The problem is that the pitch of the LED panels, so the LED panels they use are surprisingly low resolution. Okay, we're talking like 300 pixels by 200 pixels, which is a bit ridiculous. you can see the pixels, okay? You can see the red, green, and light. You don't have to be very close to it, like it's very, very obvious very quickly. And so because the pitch is quite wide, you have a problem of aliasing, so it's a sampling of your camera that interferes with the sampling of the screen, and you have frequency overlaps. Classic signal processing problem that creates this kind of weird patterns you can see, hopefully here. And the way they deal with that is, well, they kind of have to live with it, okay? And they usually, what they do, they take a fast-ish lens, and they're going to defocus the lens to create a bit of blur in the background. So the first thing they do is, like, they have pristine quality, but the first thing they do is to blur as much as they can of the background, which gives us some hope that we can do some job here. So aliasing is a big problem. Latency, obviously, is a problem. They're trying to reduce latency as much as they can. Genlock, we mentioned, in theory, this is a solved problem. In practice, of course, it's not. And color calibration being one of the big problems. Something that we're working with them on is the fact that LED panels, if you film them from an angle, you have different colors, like you have different color shift from the bottom left to the bottom right, the top right. It's not the same kind of color degradation you have, so it's a mess. This is aliasing in real life, but this is a bit pushed, this is a bit extreme, okay? But this, if you don't use defocus or anything like that, this is what you observe on the screen. You have this kind of pattern that gets overlaid on your film. All right, so how did we do? Some graphs. All right, so what you're looking at here is the RD curves for 3 of the different scenes we tested on. And what you compare, oh yeah, that's must be it. Yes. Okay, so when you're looking, the HAP is the black dot here, okay, so black dot here. And the brown one is notch LC, so these are the reference, the near lossless intermediate file format they're using, right? And the AV1 is the green curve here, all right? And so what we're looking here is at a VMAF of 90, which is kind of the best we could use. This is the on-disk VMAF. So this means like this is the classic stuff you use too. So we just took the material offline and we just did the RD curves offline. And we have the usual metrics here that at VMAF 90, we get about from 10 to hundreds of times bitrate savings. Now, when we have a screen in between and we record that, things drop, okay? And that's because if you film something, you're going to have some noise in the process, right? And so just even 2 recordings of the same thing will create an error. So you cannot get infinite PSNR by just comparing your reference against your compressed one. It's because, well, you have a physical process here, and therefore you always have some noise. And this is the reason why going from the raw footage to the actual recorded footage, you have a drop in the quality. But in that settings, we still observe that AV1 gives us anything from 2 to 50 times bitrate savings at still hitting the VMAF 90, which is to show that for our purposes, this is all fine. This is an example. Don't mind, this is like encoded using GIF to make it work on Google Slides, but this is just a detail we're looking at. And the main point we want to make here is that on the left, here's the near perfect one, notch LC, and AV1 is on the right. Quality is the same, but we have almost half the bit rates, so we should be happy. Quality still looks kind of dodgy, but remember, there are issues with these setups anyway, so it's kind of complicated. Right, so yes, it works. But now the problem we have is that they want things to work very fast, and they can't really afford to hit the particular VMAF target they want. Okay, so in their problems, they really need to hit a particular VMAF quality, and so just to try to trick the QP parameters is a bit of a problem. And now Vibhoothi will explain to you this second part of the talk, which started something very generic that applies to any problem, including yours, but that is specific to also to virtual production here, because we want to be able to hit particular quality constraints.
All right, thanks, François, for the introduction and baseline for how it looks, so it's easy for me to talk. So what we are doing here is that we call it Light VPNet. It's just a name. It's like a classic pipeline on how you do it. So you have an input video here, and we have a bunch of feature description, which is trying to explain how it goes, and it goes to some neural network, and it predicts bunch of QPs. So it's a very classic thing which happens everywhere. So what we do here is that let's take a look into this part. So again, our goal is to predict a particular encoding settings to hit a target VMAF score, because we are using VMAF here as reference. So again, the features here is that quite straightforward. So we want to have some video level statistics. So, and then this video level statistics is extracted using a fast hardware encoder. And we are using NVIDIA AV1 encoder, because in VP world they use NVIDIA hardware encoder, so we can use that. And we use inspect tool to extract frame level and video level statistics. And for video complexity, we are using VCA, which is video complexity analyzer, which uses fast DCT to compute spatial information, and a temporal information, which is just a difference from previous frame. Again, it's quite straightforward features. And again, last thing which is unique in our case is like we have semantic features, which is using clip from OpenAI. So we extract a semantic feature per frame for first 8 frames, and we put that to a small neural network to normalize them. So I'll get into details to that quickly. And the output which we are doing is that we want to have multiple targets so that it's applicable to different use cases. And we know that a non-neural network is perfect, so we try to predict different QPs to hit different targets. So in our use case, we have 8 as the target QPs here, ranging from VMAF 80 to VMAF 99, because that's the point of interest in our use case. And we have a ground truth QP, which is like 24 points, and we use P-chip interpolation to interpolate between these points. Again, talking about the network part, again, it's quite straightforward, simple network. We have the main network is like a 4 dense layer network, which uses batch norm, GELU, activation, and dropout, and we have a residual connection. And for the mini CNN, which we are talking about, again, like I remember the clip thing which I mentioned, it gives a 512 by 8 as the vector per frame, so it's like a 4096 vector. So we try to feed that to a small neural network which is attention based, so it takes these features, tries to make a 16:1 embedding, which is jointly trained with the main network, so that we can have some meaningful representation of the content. Again, in total we have slightly less than 1 million parameter. And for the data set, it's actually we have a 1080p classic data set, which is publicly available with bunch of open content, and also some test footages from Sony, Arri, and other camera vendors. And you can check our project page to get more information. Again, it's so in this test, to make it slightly more easy to understand, we have 1080p resolutions only, and the frame rate goes from 24 to 60. And to give a performance idea, remember we have what this network will give us like 8 QP points. So the mean performance across all target VMAF scores is around 4.47. And remember, as this is the hardware encoder, we have the QP range to be between 0 and 255. And in terms of VMAF performance, it's slightly under 1 VMAF. And when we see the performance, we see that we can achieve around for 87% of our test cases, we hit our target VMAF. And when we measure this VMAF error for this 87%, we try to have it a threshold of 2, because it's easier to have it within 2. And now we can look this result in a slightly different way. So as we know that we have different use cases, and we have a strict requirement to hit a certain VMAF score. So what we see here is that we try to take the video, we try to put to our prediction network, get the prediction, and then see whether we are close to the target VMAF or not. So if it's not close to VMAF, we try to take the next QP which is being predicted and try to see whether that can hit the target VMAF score or not. So let me take you through the graph. So again, we had three methods. One is the fixed QP. Here we have static QP, which is 8 QPs, which is on average used to hit the target VMAF score which we want. And practice, it may not hit because of different content complexities. So that's the fixed QP, which is represented in green color. And here the x-axis is talking about average extra encodes. That is that you try to use the prediction. If it's not using that, you take the next QP level. So on average, how much you need that for our test data set. And with this, red color, it uses JTPS method, which is a method which uses VCA features and some bitstream metadata and feeds that to a random forest regression. And that's the method. So we use that to compare. That's represented here. And the third one is the light VPNet. And remember, like different shape represent different VMAF targets. For example, we are targeting VMAF 91 here. So first point we need to see is that the y-axis is a bitrate here, right? So we can see that from between two methods. So here the bitrate is pretty similar and it's around 40 kilobits between both. So that gives us some confidence that the bitrates are quite similar. And then if we look at JTPS, it's actually pretty good. We get around 0.6 times lower encode, and it's around slightly less than 0.4 as extra re-encode. While when we go to light VPNet, when we use our method, it's around, we only need 1 out of 10 re-encodes in this case. So that's one part, and now we need to look into, we get these results, and now we need to see whether, how does the feature actually, which features actually matter. We have a large feature vector like 754 by 1. Is this actually noise or is it actually contributing? So we did a quick ablation study, and what we compared is that we used light VPNet and then we removed PCA and then we removed Clippy and then we removed both and see how it impacts. And we can see that for the light VPNet we remember this 0.08 is coming from here, which is like 0.08 is the average re-encode which is required for VMAF 91. And when we remove VCA, it's around 0.13, and with Clippy, it's 0.17. It's actually almost twice when we compare with our results. So that's our main key takeaway, that Clippy is actually contributing and other features are also contributing. And talking about the complexity, we try to do an end-to-end analysis of the complexity, and we observe that the end-to-end analysis, it's around 3 seconds from taking any video, downsampling, prediction, and getting the result, while JTPS is around closer to 6 seconds. Yeah, so that's the main here. So what we observe that with the we could actually use AV1 in the VP environment, and we can get around 10 to 50 times bitrate savings. And with a prediction network, we could actually reduce the amount of re-encodes required. And in terms of VMAF error, we are under 1 VMAF error. And again, the data set is around 1080p videos with thousands of videos. We need to scale it more and have more resolutions to make it more generalizable. And that's it, mainly from us. And we'll be presenting this work in PCS later this year. So yeah, I'm happy to take a few questions if you have time.
We're slightly behind the schedule, so let's go for the coffee break. For the question, please ask during coffee break.
I have short, but for virtual production, because sometimes they are using also, as we see on this slide, curving. So how do we deal with the curving cases? And another trick that is in use also is to keep the possibility to do the kind of a green screen. You double the frame rate, and you still have that. So are you dealing also with this type of problem, or?
So we're not dealing with that in the AV1 format, okay? But yes, that's something, the crazy stuff they do, like they have burst of frame rates, and then one in 10 frames they just have splice green screen just to.
So that's
yeah,
additional problem.
Yeah,
Okay.
it's additional problem.
Okay.
But that's more for the people in the audience, so that's not our problem. You know.
And for Vibhoothi, I would have loved to see an ablation study to see the importance of clip features, the semantic features that you are using, what it brings in the model. But this we can discuss at the coffee break. Yeah.
Yeah.